Hi, and welcome to today's lesson. Today we're going to be talking about applications of the definite integral. Let's now talk about the applications of integration. And I've hinted at this before. We talked about how the derivative, when you hear the word derivative, you should always be thinking of the slope of the tangent to the curve at a certain point. Well, when you hear integration, you should be thinking the area under a curve. And how does this all work? Well, let's consider this curve y equals x squared for x is greater than 0. And I've drawn it in three separate graphs here, where this is the y-axis and this is the x-axis. Well, if I want to approximate the area under the curve from 0 to 3, I can use lower rectangles. And when I make the lower rectangles from 1 and from 2, I see I only get 2 rectangles, and you can see that this underestimates the area under the curve because we're left with this white area here that's less than the actual area. If I consider the upper rectangles from going up from 1 and taking a left and making 3 different rectangles, well, I also get an estimate of the area under the curve, but I overestimate that area because these red areas above the curve are extra. And in green over here we have the exact area. Well, if we increase the number of rectangles from 2 or 3 up to 10, 20, 100, the number of rectangles n is getting higher and higher, and our approximation is getting better and better. So we can say that the lower sum, or the sum of the lower rectangles, and the sum of the upper rectangles, from here is our lower rectangles, and here is the upper rectangles, we have the area, the exact area, right in the middle between lower rectangles and upper rectangles. But if I take the limit of n going to infinity, and the limit of n going to infinity. What is n? N is the number of rectangles. Here I had 2 and here I had 3. If I increase that number of rectangles towards infinity, eventually the little area below the rectangles here goes to almost 0. And the little area here above these rectangles goes to almost 0. So we can say as I take infinite rectangles, the upper sum goes down towards the exact area, and the lower sums goes up towards the exact area. Continuing on with our discussion of the definite integral, providing a number which represents the area beneath the curve, let's consider this curve here f of x, and I'm integrating from a to b, and of course that means I'm going to split my curve up into many little rectangles, and I've taken one rectangle here. If this is x on the x-axis, what is the function value of x? It's going to be f of x. We see over here, we have a point x, f of x. And here, I've got x plus dx, so therefore here I've got f of x plus dx. Well, if I'm looking at all of these triangles and I take the lower triangles, meaning I go over x and up f of x, then my height here is f of x. And my width of the rectangle here is dx. So if I want the area of this one particular rectangle, if I move that across there, that rectangle there is going to be f of x times dx. Well, the area under the curve from a to b will be the sum of all of the little rectangles from a to b. Of course, that depends on how many rectangles you have. Well, how many rectangles do we want? We want dx to go towards 0. We want that limit, as dx is the width of each of these rectangles. We want dx to be going towards 0, to be very small. And what are we doing? We're taking the sum of f of x times dx. Well, what is f of x times dx? It's simply base times height of a rectangle. So we're taking the sum of those rectangles, the area of those rectangles from a to b. Another way to say that would be from a to b, f of x dx. You can see why I get frustrated if you don't write that dx there, because that is actually the width of each of these little rectangles. So here is our official statement for integration and area beneath the curve. The definite integral provides a numerical value whose geometric interpretation is connected to the area enclosed by a curve, f of x, the x-axis, that's very important, that it's this axis here, the curve, and the vertical lines x equals a and x equals b. Furthermore, continuing on with applications of integration, we see that if y is equal to f of x and is positive and continuous, positive means our graph lies above the x-axis. That's so important when considering integration is where is the curve? Is it above or below the x-axis? Provided our curve y equals f of x is above the x-axis and it's continuous, meaning we don't have to pick up our pencil, on the interval from a to b, x equals a inclusive to b inclusive, means it can equal a and it can also equal b, the area a square units bound by our curve f of x, the x-axis here, x equals a and x equals b, is given by the definite integral from a to b of f of x dx. We can make a further observation about areas. For example, to find the area bounded by the curve y equals f of x, here is that curve, the y-axis, which is the vertical axis, y equals a, the lower bound, and y equals b, the upper bound. First step, solve for x. We have to get x all alone. Then, in our second step, we find the definite integral of a to b of whatever x equals with respect to dy. Now, we can think of taking our rectangles this way, and each of the widths of the rectangle is dy. First step, solve for x. Whatever x equals, we're going to integrate that with respect to y. Let's do an example. Here's an example that illustrates that point. Find the area enclosed by the curve y equals the square root of x. The y-axis, the lines y equals 1, which is a horizontal line, and y equals 3, which is another horizontal line. First step, solve for x. We know that this is y is equal to x to the 1/2, so we can square both sides and we get x is equal to y squared. There's our first step. We solve for x. Now integrate with respect to y. So we're going to integrate from 1 to 3, lower limit to upper limit, of y squared dy, and that will give us that area. Of course, the same rules of integration apply. This will be y to the third divided by 3 from 1 to 3. We can substitute a 3 in there. So if I substitute a 3 in there, 3 cubed divided by 3 is 9 minus 1 cubed divided by 3 is 1/3. Gives us a total of 8 2/3 square units for the area here. Let's now talk about negative values for the function. If f of x is a negative number over the interval x equals a to x equals b, so if I have a picture of this like this, where somewhere from a to b, we'll call this a and this b, somewhere from a to b our function dips below the x-axis. In other words, f of x, another word for that is y. The y value for x between a and b, the y value is less than 0. In other words, we're dipping below the x-axis because here is y, or f of x. If that is below 0, that means our function value is negative. If our function value is negative, then when we take the area, when we integrate this, we get a negative number. So if I integrate it from a to b here, and I'm looking for this striped area here, I'm going to get a negative number. Therefore, if we want to write the area, we have to consider that we're going to take the opposite of the negative area. Another way to think of that is take the absolute value of the integral. And of course the integral represents the area under the curve. Area under the curve if we're talking about a positive function value. But really it's area trapped between our curve and the x-axis. If our curve is positive or above the x-axis, our areas will be positive. If our curve is negative or below the x-axis, we'll get a negative value for here. So if we want to deal with this, we have to consider its absolute value or just take the opposite of that particular definite integral.